Hello, welcome to another module in this massive open online course. So, we are looking at schemes or techniques for compressive sensing, and we have seen that orthogonal matching pursuit for compressive sensing, alright, basically for sparse signal recovery, that is to estimate a sparse signal x bar, alright. So, we have seen this algorithm in the previous module. Let us now look at an example to understand this better. So, what we want to look at is the orthogonal matching pursuit. We have already seen the orthogonal matching pursuit. So, now what we want to see is an example, a simple example, a paper and pen kind of example for the orthogonal matching pursuit. And let us consider the following example. We have y bar equals phi x bar, we have to estimate the vector x bar. So, let us consider the example that is given as follows. The vector y is 0, 2, 3 and 5, and the matrix phi is the following. This is 1, 0, 1, 0, 0, 1, this is 0, 1, 1, 0, 0, 1, this is the third row 1, 0, 0, 1, 1, 0, and the fourth row is 0, 1, 0, 0, 1, 1 times the vector x bar, which is basically x1, x2, x3, x4, x5. So, this is your y bar, this is your dictionary of sensing matrix phi, this is your matrix x bar, and so the various parameters of this are as follows. This y is a 4 cross 1 vector, the matrix phi is 4 cross 6 and x bar is 6 cross 1, and therefore, in this problem we have m equals 4, which is basically the number of equations, and n equals 6, which is the number of unknowns, and we can see m less than n, which implies number of equations less than number of unknowns, and therefore, to estimate x bar, or basically to recover x bar, alright, with x bar, remember you cannot use conventional linear algebra, basically because in linear algebra you need at least number of equations, or number of equations equal to the number of unknowns, or the number of equations at least equal to the number of unknowns to uniquely determine the unknown vector x bar, and therefore, one has to enforce some other condition on x bar to uniquely recover it, and the condition that we have seen so far, that is to enforce sparsity, that is to determine a sparse vector x bar that satisfies this system of equations, alright. So, or that fits this model. So, we assume that x bar is sparse, and then we want to estimate this sparse vector. And this is basically what is termed as sparse signal recovery. This is termed as sparse signal recovery, and the algorithm we have seen OMP for sparse signal recovery, that proceeds as follows. First, find the projection. So, you can see these are the columns. Now, remember when you talk this y bar, these are the columns. For instance, this is phi 1 tilde, this is phi 2 tilde and so on and so forth. This is phi n tilde, or in this case n equal to 6. So, this is phi 6 tilde. So, what we will do is we will find, so OMP, remember the first iteration, you find the projection of x bar on each column of the matrix phi, which is on each phi I tilde, and choose the column which yields the largest projection, alright. So, remember you have I1 equals argmax j, in fact 1 less than equal to j less than equal to n magnitude phi I tilde transpose times x bar, okay. And remember is, and what we can, and this we can do as the following thing. So, so basically what we are doing is finding projection of, or find projection of each or find projection of x bar on each column of phi. This can be done as follows. What we are going to do, or find projection of y bar, I am sorry, find projection of y bar on each column of phi, and what we, this can be done as follows. So, what we are going to do is we are simply going to perform phi transpose y bar. What that gives us is, that gives us basically the inner product of each phi 1 tilde phi 1 tilde transpose, phi 2 tilde transpose, phi n tilde transpose y bar, which is basically nothing but, if you look at this, this is basically phi 1 tilde transpose up to phi n tilde transpose into y bar. So, each of these entries corresponds to, so each entry equals projection of y bar on column of phi. Now, the other thing that you must have observed is, if you look at these rows, you can see that these rows are random zeros and ones. So, these are noise like waveforms, okay. So, that is other important thing. So, rows of phi are random zero column. So, these are noiseless. Remember, that is an important criteria. Remember, you cannot take time domain or spatial domain measurements, but you have to take the projections of x bar on random noise like waveforms, alright. Each measurement is basically, each observation is a projection of y bar on this noise like waveform, okay. So, now let us find phi transpose y bar. Phi transpose y bar, remember phi transpose is this matrix in which the rows become columns and the columns become rows. So, first row will be 1 0 1 0 0 1 0 1 1 1 0 0 0 1 1 0 0 0 1 1 1 0 0 1, and you take the projection of y bar. So, that is 0 2 3 5, and if you compute this, if you evaluate this, you will get the vector 3 7 2 5 8 5. Remember, each of these entries is the projection. For instance, 3, this is equal to phi 1 tilde transpose y bar, 7 equals phi 2 tilde transpose y bar, and so on. And if you see, the maximum occurs equals fifth entry or fifth component, which is equal to phi tilde transpose y bar. Therefore, the maximum projection of y bar has the maximum projection along column 5, that is corresponds to phi tilde 5. Okay. Therefore, and therefore, now we form the basis matrix using this column phi tilde, or in other words, what we are saying is this quantity I1, that is the index of the column which has the maximum projection, that is phi. So, this is phi tilde of I1, which is basically phi tilde of phi, that is your basis matrix, which is basically, that is nothing but this, you take the fifth column of the matrix phi, and that will be fifth column of matrix phi, that will be 0 0 1 1. Okay. So, this is the fifth column of, and now you solve the least squares problem, y bar minus a1 x bar. Remember, this is the first iteration. So, you solve the least squares problem. And once you solve this least squares problem, remember the solution to this is x hat 1 equals a1 transpose a1 inverse a1 transpose y bar, which is a1 transpose. Remember, a1 0 0 1 1. So, this is 0 0 1 1 transpose, very simple, simply row vector transpose the column vector 0 0 1 1 inverse of this times a1 transpose 0 0 1 1 times 0 2 3 5. Okay. And this will be half, because a1 transpose a1, this is row vector times the column vector will be 2. So, inverse of that is half times 0 0 1 1 times 0 2 3 5. So, this will be half into 8 equal to 4. Okay. So, this is basically your x hat 1. Okay. So, that is basically your estimate of the sparse vector in the first iteration. Remember, this x hat 1 corresponds to the index of the column that is chosen in the first iteration, that is column number 5. Okay. So, your sparse vector, so this entry corresponds to the fifth column or the fifth entry of the vector x bar. Okay. Now, what we will do is we will find the residue after the first iteration. Okay. So, now find the residue. So, this is the estimate . And now what we will do is we will find the residue for the first iteration, and the residue is R1 or rather r bar 1 y bar minus a1 x hat 1, which is 0 3 5 minus a1 is simply the column 0 0 into 4. So, this will be basically 0 2 minus 1 comma 0 2 minus 1 this is the residue in first iteration. Okay, this is the residue after the first iteration, and this is in fact what we carry over to the second iteration. Remember, subsequently find the projections of the columns of phi on this residue, choose the one that has the maximum, repeat the process, least square solution, alright, find the residue, repeat the process. Okay. Now let us go to the second iteration. Okay. So let us look at now second iteration. In second iteration, we find projection of r bar 1, that is residue from first iteration on each column of phi. Okay. And therefore, again similarly what we will do phi transpose r bar 1, which will basically give the projection of the residue on each column of phi. Okay. So, this will be 1 0 1 0 0 1 0 1 1 1 0 0 0 1 1 0 0 0 1 1 1 0 0 1 on the residue 0 2 minus 1 1. Okay. Now you take this projection, you evaluate this, you will see that this comes down to minus 1 3 2 1 0 1, and what you observe that now the maximum is 3. Maximum corresponds to second column. This is basically phi 2 tilde transpose r bar 1. So, the maximum entry corresponds to the projection of the residue r bar 1 on the second column, that is phi 2 tilde transpose r bar 1. Therefore, now you choose the second column, you make the augmented matrix. So, the augmented matrix becomes previously we had phi 2 tilde, now we are writing phi 2. Now remember, you can also write it as phi tilde comma phi 2 tilde, it does not matter, as long as you are clear that this is the order, and therefore corresponding the entries of x tilde will x hat will correspond to these two columns. Okay. So basically your matrix, in fact I should write it like this, these are simply the columns of the matrix. Okay. So you have matrix, you are picking the columns phi tilde, phi 2 tilde, phi tilde, and these will be. So this is basically what it says is I2, that is the index picked up in the second iteration is basically 2. Okay. And the columns, corresponding columns are 0 1 0 1 and 0 0 1 1, and now you again solve the least squares problem. Now you have the estimate x hat, which is basically you solve the least squares problem norm y bar minus a2 second iteration x bar 2 whole square. This is the least squares problem. Remember, this is your you can call this as the augmented basis matrix, okay. And once you solve this least squares problem, what you get is x hat 2 equals a2 transpose a2 inverse a2 transpose y bar, which is basically, if you look at a2 transpose, that is 0 1 0 1 0 0 1 1 times 0 1 0 1 0 0 1 1 a2 transpose a2 into inverse into a2 transpose, once again 0 1 0 1 0 0 1 1 into y bar, which is 0 2 3 5, which basically equals, this is 2, this is 1 1 2 inverse of this matrix times 0 1 0 1 0 0 1 1 times y bar 0 2 3 5, that will be basically 7 8, and inverse of this 2 cross 2 matrix is very simple. You interchange the diagonal elements, which are the same, negative of the off diagonal elements, and you divide by the determinant 1 by 4 minus 1, which is 3 times 7 8. So, this is 1 by 3 times 16 minus 7 is 9, or I am sorry, 14 minus 8 is 6, 16 minus 7 is 9, and this will given now give us 2 3, very simple. And this is basically, this is nothing but your x hat 2, estimate of x hat 2, estimate in the second iteration. This is the estimate in the second iteration, and now of course we again need to find the residue, that is r bar 2 equals y bar minus a2 x hat 2. This will be 0 2 3 5 minus a2, which is 0 1 0 1 0 0 1 1 2 3, and you can calculate this, and what you will see is this residue is exactly 0. Residue equal to 0. This is your r bar 2. So, r bar 2, so the residue equals 0, which basically means that you are exactly able to exactly approximate y bar in the second iteration, which means you are using the basis matrix in the second iteration, that is comprises of the columns phi 2 tilde and phi phi tilde. Therefore, your x hat 2 or the second iteration, and what we have is y bar equals a2 which basically has two columns phi 2 tilde phi tilde into x2. So, this is able to exactly approximates y bar, and therefore residue is 0, no further iterations are needed. So, which means if you look at x hat of 2, which is equal to 2 comma 3, 2 corresponds to, remember, each corresponds 2 corresponds to phi tilde 2, which is basically second column of phi, and 3 corresponds to phi tilde phi equals fifth column of the matrix phi. And therefore, now you can reconstruct the sparse vector x bar as follows: only the second entry will be 2 and fifth entry will be 3 and the rest of the entries are 0. So, this is second entry corresponding to phi 2 tilde, this is fifth entry corresponding to phi phi tilde, and rest of the entries are 0, rest of the entries are 0, and therefore, this is your estimate of the sparse vector x bar. Okay. And of course, as we said, this is a simple example, it is simply a paper and pen example, something that you can do on the back of an envelope kind of a calculation. Okay. But of course, problems in practice, this is just for the purpose of illustration, right. Problems in practice are frequently more complex and they will be quite involved. For instance, the size of the dictionary matrix 5 can be of the size 500 cross, let us say 10,000. Remember, the characteristic of phi, it will always have much fewer rows than columns, because the columns represent the unknowns, the rows represent the observations, alright. But you can use this OMP algorithm, scale it up and use it for similar scenarios. And as I have already said, OMP, the interesting thing about OMP is that it is a very simple algorithm. All you are doing at each stage is finding the projection of y bar, it is finding the projection of y bar or the residue on each column of phi, choosing the one that has the maximum projection, alright, computing the least squares estimate that gives you the estimate x hat corresponding to the sparse vector in that iteration, remove the current estimate, the best approximation to y bar, alright, form the residue and then continue in the subsequent iteration, alright. So, this is the OMP algorithm. This example clearly illustrates the process. Hopefully, it clarifies some of your doubts or some of how do I put it, points which are earlier lacking clarity because the algorithm was theoretical in nature. So, this algorithm sort of explicitly illustrates the OMP, the working of OMP through an example, alright. So, let us stop here and continue in the subsequent modules. Thank you very much.